As always, you have a perfect opportunity to ask your brave questions.
Boris Borisovich, I have a question.
Yeah.
How to find the covariance between a martingale and a stochastic integral? Should we transform the martingale into integral form and then
Yes,
find?
if it's possible. Yeah.
Okay.
If it's possible, yeah, because we have a theorem that says that covariance between stochastic integral and stochastic integral is integral of ordinary Riemann integral of this expected value. So you can use this property. So if you have an arbitrary martingale and the integral, there is no general formula. So if you are lucky and you can go here, then you are lucky. If not, in general, I think there are no simple answer.
Okay, thank you.
More questions?
Boris Borisovich, I have one question. What to do, for example, if our if we have in the covariance Wiener process in some power, for example, squared or cubed or in the 4 power, what should we do?
To do what? Covariance of WT with what?
With stochastic integral.
With stochastic integral, I don't see that you can have a general answer. So once again, if you are lucky, the question is like previous one. So if you are lucky, you have a theorem that if you have covariance of two stochastic integrals, then you are lucky. If you have some arbitrary process, then just try to go there, try to represent WT power 6 as a stochastic integral, maybe plus some additional term, maybe. So in general, so this is basically the same question. In general, there are no simple rules, but in general, there are no simple rules, but sometimes you can go to this covariance of two stochastic integrals. Okay.
I understood, but if we get something with, so somehow we except of the Wiener process, we weighted to the power 6 obtained the Stoch integral plus Riemann integral. So it will be impossible for us, or maybe there is some way out of the course to compute the covariance of this Riemann integral and the stochastic integral. Am I right?
About this one, WT power 6, I'm not sure that there is an actual result. It depends on the integral, because maybe the integral is easy. So obviously we can simulate on computers, but once again, there are no general formula. You ask the same thing basically for the third time. In general, there are no simple formula for this. You can simulate on computers. Sometimes you can go there and simplify it. Sometimes you can simplify that part, because, for example, if the integral in question is WU dWu, we know that it's WT squared over 2 minus T over 2, yeah? So sometimes you can either represent the left part in terms of stochastic integral. Sometimes you can simplify that integral. Maybe this integral was just integral from 0 to t 7 dwu. Yeah, in that case, I will have a 7 wt. Okay, and once again I can calculate covariance. So in general, you have no simple formula. You can simulate on computer. Sometimes you can use particularities of your left random variable and right random variable to actually calculate it without computers. But in general, there are no simple formula.
Thank you very much for answering this question, but I have additional one.
Yeah, welcome.
Can I ask it, please?
Yes. That's my main advantage over books.
So if, for instance, I received something like covariance VU, so covariance of the integral from 0 to t, VU du.
0 to t du.
Yes, and on the right side, for example, the integral from 0 to t VU dVu. So I should leave this covariance as an answer because it is not possible to distribute this covariance to open it.
I don't say so. No, my point is no. I don't say that it's impossible to calculate covariance. I say that there are no simple general formula, but sometimes you can calculate it. So, for example, in this particular case, maybe you can represent it as a stochastic integral. Maybe you can just, so what are the alternatives? So either you go here, maybe you are lucky. Yeah, either try to go there, try to transform so for example, if you have something like WT, this is my YT. So once again, sometimes you can go there. So if I take DYT, I will have T times
you will have double T dt
plus WT times dt. So my YT is an integral from 0 to t u dw plus integral from 0 to t wu du. So I may express your integral as a difference of that one and that one, and try. Covariance is a linear function. So you may try to go there. Once again, I don't say that that it's impossible to solve them. I say that there are no general simple rule, but this formula can be applied, and sometimes if you can go to that formula, you may obtain the answer. Here I see no problem. Your integral is just the difference of YT and the stochastic integral. You can calculate covariance between stochastic integrals. I see no problem because this integral is just, you can get it. We have calculated it. So it's no problem to calculate. So in this particular case, you can manage. So this is the hint. And WT is and YT is WT times T. You have other ways. So you have another way. You can go to limits. Yeah, you can can divide timeline onto n small intervals. You can calculate approximation of your process here as a discrete sum. You can calculate approximation there as a discrete sum. And basically, you can calculate covariance. Okay, so there is another approach.
Yeah, I see. Thank you
So,
very
but
much.
the first hint is sufficient, I think. I think you can just go. You have
But
there's a limit, yeah.
but in the beginning, you said that it is not there is no general formula to calculate
Yeah.
the Wiener process, the covariance of Wiener process at end stock integral, but we still receive it. And for example, if we
no, you said not Wiener process. You said Wiener process or Wiener process power 6 or so. No, in the beginning we have a recording if you like, but you said the question differently, or power 6 or something else. If you speak about Wiener process itself, that's no problem. But if you put something like very ugly, then I don't know what will you do if you have a covariance of cosine of wt power 6 times I don't know logarithm of 1 plus wt6 with. In some particular simple cases, yes, we can obtain, but when it will be some ugly function, then I'm not sure.
no, Boris Borisovich, I don't mean that you or me said different thing. I just said that if I use the first way to solve this, just have the new variable yt equal to wt multiplied by t and distribute it between the stochastic integral and just Riemann integral, and from this new equation I will get the Riemann integral and substitute it to the covariance.
The main difficulty may be that in this case we have easily guessed about we should take differential to obtain. So it was my guess that to obtain a term like wt dt, then if your guess is right, then okay. But once again, what about cosine of wt6 times logarithm of 1 plus wt6 with integral from 0 to, I don't know, wt squared plus cosine of w squared times dw. And I guess the way with limits will be also ugly. I think I see no other way as computer simulation for that guy. So it depends on the function. So if you provide simple functions, that maybe we can do it by hand, but the question was stated in the general form with a stochastic integral. With a general stochastic integral, it's hard to do it. With a stochastic integral like that, it's easy. Okay. So the point is there are no general formula, but in your particular case, it's possible. It may be possible in some other simple cases. It may be possible when two processes are represented as stochastic integrals, but in general, it may be very, very hard. Even it's possible to guess the correct. Maybe it is even possible to do it, but if we don't see so, if I write arbitrary differential equation, it's hard to, probably it will not be able, I will not be able to solve it explicitly, but even if the explicit solution exists, maybe it's hard to find it. So
Thank you very much for the
my
clarifying.
answer is, in general, it is not possible, but what you can do, you can either transform left part, either transform right part, either calculate limits, either do computer simulations. I think in general, no solution exists. Okay, let's go on. Any more questions? Okay, so let's solve some difficult exam problem. We have done with previous group. Okay, I will just open it. It's exercise number 8 from exam. Old good days when the exam was after the new year. We have a system of two stochastic differential equations. dxt is a times xt times dt minus yt times dyt. dyt is a yt dt plus xt dyt. Initial conditions are starting values are x0 and 0. And the first question is about finding the solution. Find all the solutions of the form xt is f of t cosine wt and yt is j of t sine of wt. So that's the first question. The form of the solution is given, and we need to find all solutions of this form. Okay?
Okay.
Let's do it. The strategy is very simple, but calculations are a little bit messy. Strategy is very simple. Plug in and apply Ito's lemma. Let's do it. So first I calculate dxt. dxt, according to Ito's lemma, is f prime cosine w dt minus f sine of w dw plus 1/2 minus cosine of wt times f times dwt squared, and that is dt. Okay?
Yes.
Let's calculate dyt. What is dyt? Up to you.
G prime multiplied by sinus vt dt plus g cosinus vt multiplied by t dvt plus 1/2 minus sinus vt multiplied by g and multiplied by dvt squared.
Okay, and that is also dt. Yeah, you are completely right. We simplify it. So dxt is just something times dt, something is f prime minus 1 over 2 f times cosine of w times dt minus f sine of wt dwt. The same thing for dyt is g prime minus 1 over 2 g sine of wt dt plus j cosine of wt dwt. Yeah.
Yes.
So I have applied it as lemma. Let's plug in. Let's see. I should have this answer. If I plug in dxt and dyt there, they should coincide. So if they should coincide, then so they should coincide. Basically, we have 4 equations. They should coincide. Original equation, original equation. So now I see that f prime minus 1 over 2 f cosine of wt should be equal to a xt minus f sine of wt should be equal to minus yt. So it's equation for dx. And using the same logic equation for dyt, all coefficients should be equal because it's the same process. I have j prime minus 1 over 2j times sine of wt should be equal to a yt. And finally, j cosine of wt should be equal to 2xt. Okay.
Boris Borisovich, you forgot the brackets in the first equation.
Bracket
F
first,
prime.
yes.
Yes.
Okay, now we can go on. What do we see? We see that we can equate this, we can arrange, we can express. So let's remove yt from the first. I will plug in yt there, and I will plug in xt there. Yeah. So let's do it. I will have only 2 equations left. F prime minus 1 over 2 f times cosine of wt is a times j times cosine of wt, but this should be equal for any t. And that is j prime minus 1 over 2 j times sine of wt should be equal to a times f times sine of wt for any t. But cosine of wt can be 0, yes, but not always. It's just only some points on the line. And if my function f is continuous, and it should be continuous because f prime, we have f prime, then we can cancel out cosine and sine because we should have equality for every t. So now nothing random is left. We just have an ordinary equation Okay.
Could you repeat one more time the intuition? Why can we eliminate cosine?
Because we should have equality for every t. This is not just for some t, yeah, for t equal to 5 or for t equal to 2. We should select the functions. So what is the goal of our, once again, what is the goal? The goal is to find all the solutions of this form. So what is unknown? We need to find a function f, and we need to find a function j, because the form of xt, only f and j are unknown. Yeah. So the form of x and the form of y is completely specified if we provide the functions f and j. Okay.
Okay, yes, it's clear.
So we need, so this, when I write equation, it means for every t, I don't even add this this comment that for every t, yeah? And this equation is also for every t, for every t, for every t, for every t, for t equal to 5, for t equal to 6, for it, but cosine of wt, it can be 0, but only in some points. So yes, what is the plot of wt? The plot of wt is something like this. Yeah. When cosine is 0, cosine is 0 at some discrete moments of time, because to make cosine 0, you should have wt equal to pi over 2 plus pi n. Yeah. So if wt is pi over 2 plus pi n, then cosine of wt is 0. Yeah. So these are some lines. So at these points, cosine of Wiener process is 0. Yeah. At all these points, cosine of Wiener process. Okay.
Yes, yes.
There are many points where cosine, all these points, cosine is 0.
Not really.
So, sorry, not really. Why?
A few points.
Sorry.
No.
There are a lot of points. But anyway, if you look around each point, then you will find plenty points where cosine is not 0. Yeah.
Yes.
But that should be for every t. For every t. And yeah.
I see. That's why we just remove it.
Yeah. Because yeah, in some points it would happen occasionally, just because wt is equal to pi over 2 plus pi n. But to make this equal for all points, we need to choose f prime minus f equal to aj. Okay, let's go on. Now nothing random, so we are happy. Nothing random, no Ito's lemma, no Wiener process, nothing random, just ordinary differential equations. So we can just express j, plug in there, plug in here, and obtain an equation for f. So just, let's say 3 minutes, just what is the equation for f? Equation for f. So it's up to you. Just derive the equation for f.
May I try?
Yeah, obviously.
F2 prime minus 1 over 2 f prime minus
Just a moment. You're too fast. Chpink. Yes, I'm ready. F prime prime.
minus 1 over 2 f prime minus 1 over 2 bracket f prime minus 1 over 2 f bracket closed plus a squared f. No?
Yeah, I think that's right. So we have, let's move on. We have f prime prime minus f minus
1 over 2.
1 over 4, I think. Because you, oops, because you have 1 over 2, it's 1 over 4 plus a squared. Squared plus 1 over 4 f, that is, yeah, like this, or plus, yeah?
Yeah.
Okay? Okay, how do we solve it?
Using polynomials, no? Like r squared minus.
Yeah, we have lambda squared minus lambda plus a squared plus 1 over 4 times 1. What are the roots?
Excuse me, shouldn't there be minus inside the brackets? Like a squared minus 1/4?
No, it's minus minus, so it's plus.
I got plus as well. I got discriminant, which is negative. Is it okay?
Okay.
It's minus 4a squared.
Okay, minus 4a squared. And we can easily solve it. So it's plus or minus 2ia squared. Yeah, if you take a complex number squared, you will get minus 4a squared, get 2 minus 2ai squared, you will get minus 4a squared. Yes, it's not that, it's minus 2.
Boris Borisovich, may I have a may I ask you about the previous page? So the question is about the last row. Yes, shouldn't be here minus a squared f.
Let's check.
I just got minus a squared too, and that's why I asked about the sign in the brackets.
Okay, let's check. So let's multiply by a squared. Yeah. Let's multiply by a squared. So I get a j squared minus 1 over 2 aj minus a squared f equal to 0. So I have, this is aj minus 1 over 2j. So yeah, I think it's minus f squared. Okay. Yeah, let's check aj strings. It is aj prime. This is aj. Yeah, that's okay. Let's check here. F minus aj. Y is f sine, yeah. Y is f sine. Yeah, I think that's okay. Yeah, we need to correct. Who has done by himself or herself? Okay, you are silent. Yeah, let's go on. So it will be what we will get here. So let me check, because with previous group, but it's okay for online that no one.
I have found a mistake because I have minus FA. That's why I got plus A squared F. But I can't, I did it on my own. That's why I can't find mistake in your notes.
Maybe
the previous group we accidentally skipped minus in one equation when we
okay,
connected to a
so let's
plus.
continue with this idea. So okay, it's up to you to check. I'm okay with that. Not everything is right. Up to misprints, the idea is fine. F, I will have what? 1 minus a squared, yeah? So what will change?
1/4.
1 plus or 1 minus?
1/4.
Ah, 1/4. Yeah, okay. So, but that's strange. That's very strange. We should have cosine there. Okay, but nevertheless. So let's go on. 1 over 4. Ah, but it's okay. Yeah, that's fine. Discriminant will be 1 minus 4 times 1 over 2 minus a squared. So it will be 4a squared. So it will be 2a plus or minus without complex. So that's the same thing, but without complex numbers. Okay. So we will have a general solution f of t is equal to c1 times cosine of 2a. Oh, sorry, exponent of 2at plus c2 exponent of minus 2at. Okay.
Yes.
Yeah, that's easy, but okay. So now we have a solution. Yeah. Xt is just Let me open the text because it's very long to change. Takes a long time to change the page. It's C1 exponent of 2at plus C2 exponent of minus 2at times cosine of wt, and yt is j times sine of WT, and J, according to our substitution, is just F prime minus 1 over 2 F divided by A, yeah? Something like that.
Yes.
Multiplied by sine of WT. And it will be what? It will be pim. It will be, yeah, let's take the derivative. We cannot do it without. It will be C1 times 2A exponent of 2AT plus C2 times minus 2A exponent of minus 2AT minus 1 over 2F divided by A times sine of WT. We go on and we get C1 exponent of 2AT plus, no, 2 minus 2C2 exponent of minus 2AT. What else? Yeah, let me write a little bit differently. Let me write like, what will be with exponent of 2AT? What do I have? I have 2C1 minus C1 over 2A. What will be the term before exponent of minus 2AT?
It's minus 2C2 minus 1 over 2A C2.
Minus C2 over 2A, yeah?
Yes.
Okay, so we have solved. We need to recover C1 and C2 if possible from initial conditions. Initial conditions are x0 is x0 and y0 is 0. So sine of W0 is 0. So this condition will give us no new equations. But then one is okay. If I plug 0 in x, I will obtain x0 is C1 plus C2. Okay. So I get only one equation. Yeah.
Yes.
And now we have let's remove it. Let's remove it. Say C2. C2 is x0 minus C1. So we will remove C2 from initial conditions. So we have xt is C1 exponent 2AT plus x0 minus C1 exponent of minus 2AT times cosine of WT. And finally, YT, we do the same thing. It's C1 times exponent of 2AT times 1 minus 1 over 2A plus x0 minus C1 times exponent of minus 2AT times, what will I have there? Minus 2 minus 1 over 2a, and multiplied by sine of wt. Okay, now we have solved it. With previous group, we have a different result, but I think only one is correct. I think so. We have another solution for another equation for f prime. So it was a little bit different. So there may be a mistake with sign here or there. Check carefully. Check carefully. A mistake in sign is probable, but maybe it was with the previous group. With sign is probable. But the logic of solution is the same. So it doesn't affect the logic of solution. But instead of different real roots, with previous group, we received 2 complex conjugate roots. And so we received cosine and sine inside. I like this better. Okay, let's move on. The point B says consider dt that is xt squared plus yt squared, and check whether it is non-stochastic for any solution. We will do the same strategy. We will use the same idea, just Ito's lemma and plug in. No more ideas. Very simple approach. Just plug in and Ito's lemma. So let's apply Ito's lemma first. It's 2xt dxt plus second derivative of it, 1 over 2 times 2 times dxt squared, plus I go on with the second term, 2yt dyt plus 1 over 2 times 2 times dyt squared. Okay?
Boris, can I ask a question?
Yeah.
Will there be a cross derivative term?
Yes, but it's 0.
Why?
Sorry?
Why it's 0?
And why not?
And
Where
why
is
yes?
d dx dy? I think it's 0. Just look at the function.
Yeah, that makes sense. Exactly. Thank you.
Because there are no the cross derivative.
Yes, yeah.
So, but it should be no. So, no. Normally, you are right. In Ito's lemma, you can. Yeah, in some sense, you are right that we should have 1 over 2 times 2 times d. So, in general, so if instead of a plus, we have a minus, then you are right. Yeah, we should have it. Maybe it's worth mentioning that normally we have it. Yeah, for general case, we have it. You're right that it's better to mention it to avoid mistakes on the exam that in case of dt equal to xt squared times yt squared, you will have a cross term. But in my particular case, I do not have it because derivative is 0. Okay?
Yeah, okay, thank you.
So now we just plug in. So we have applied it as lemma. Now we just plug in. We have expression for dxt. We have expression for dxt, for dyt. For dyt, we have in our original problem. We just apply it. So dt equals to 2xt times, what is dxt? Axt dt minus yt dwt plus 1/2 times 2 plus, or multiply yt dwt squared. So now terms with dy. 2yt ayt dt plus xt dwt plus 1/2 times 2 times ayt dt plus xt dwt squared plus 0 cross derivatives. Okay, simplify it. You have, let's say, 3 minutes to just simplify it.
Boris Borisovich, may I ask a question, please?
Yeah.
How do you understand that there should be a cross derivative?
Just it as lemma. Just it as lemma. What does it say? Take Taylor expansion and kill every term using simple rules. So what's basically it as lemma? It says takes Taylor expansion and use simple rules like dt times dt is 0. So what is it as lemma? So it says basically Taylor expansion plus Taylor expansion. So I would say it as lemma is just like that. But I work with Ito's process. Every Ito's process is a sum of Ito's integral and Riemann integral. So dxt is something times dt plus something times dwt. dyt is something times dt plus something times dwt. So in Taylor expansion, normally, I would have all terms 4th, 5th, power 6, power 7th, power, so I will have a lot of terms. But if I take dxt cube, I will have that guy cube, and their product. So every term will be 0, 0, okay? But if I have, so this is 0. If I have dx times dyt, this term, that is not 0. So if it will be a t bt ct dt. So in this case, I will have bt times dt times dwt squared, and it is not 0. So basically, what is it as lemma, and how it's proved? We will not prove it, but basically the intuition behind it is very simple. Every function, even of 2 variables, of 5 variables, if it's a good function, it can be decomposed into Taylor expansion. If we work with sums of Wiener process, then we have these limits. And basically, in Taylor expansion, every term except 4th and 2nd will disappear. Okay.
Yes. Thank you very much for the explanation. Now it's very clear. Thank you.
So normally I should have also something like third derivative of d with respect to x times dxt squared, and will be 1 over 3 factorial. So in Taylor expansion, I have term like this, but this is 0.
Clear.
So there are many terms, but all of them are 0 except first and second. Okay, so now you simplify, and what do you get after simplification?
yt squared dt, xt squared dt,
Sorry,
plus
sorry. Once again.
yt squared dt plus
Let's
x
move
squared.
dt at the end.
Okay, plus xt squared plus 2a xt squared plus 2a yt squared. And that's all.
Okay.
No?
And that's times dt. So I see that the answer is like this. Is d dt is equal to 1 plus 2a times xt squared plus yt squared times dt. But this is dt. So my d dt is 1 plus 2a dt dt. And basically that means that dt, yeah, it's 1 plus 2a dt. So basically derivative is a proportional to a function. So dt is d0 times exponent of 1 plus 2a. So there are nothing stochastic. So I can even write the full expression. Dt is x0 squared times exponent of 1 plus 2a. So there is, oh, sorry, I forgot t here. T. Yeah. So there are nothing stochastic. Okay, so the question was to check whether dt is stochastic or non-stochastic. So dt is deterministic. That's okay?
Yes.
Deterministic in the sense that if we know d0, then we can determine dt at any d at any period of time, right?
Yeah. It's non-random. And we can draw some conclusion about what happens with x and t. So basically it's a we can just say that we can describe our process a little bit. So dt is non-random. What does it mean? It means that if we draw circles, that we know that our process will be on this circle at time t equal, let's say, to 4. Our process will be on that circle at time t equal to 3. So we can predict the distance from origin of our stochastic process. but we cannot say exactly at which angle our point will be located. So it is something like it moves randomly, but the distance from origin, yeah, dt is just a squared distance from origin. The squared distance from origin is completely predictable, but the exact place is not. Okay?
Mhm.
So just about the what is our conclusion about the behavior of the process. So the distance from origin is predictable, but the exact place of our particle xt yt is not predictable.
So, in other words, if we have two stochastic processes, if we combine them in a particular way, we can get non-stochastic one.
Yes, obviously. Sometimes, not always, but yes. So if you have xt and xt, if you combine them in that way, you will have a non-stochastic zero. Sometimes yes, sometimes not. If you have two stochastic processes, one is a copy of the other. If you take the difference, you will get zero. Yeah, that's obvious.
Boris Borisovich,
Yeah.
may I ask a question, please?
Yes.
So we do not know the exact place, or we do not know the trajectory. For instance, we have a point t equals to 3, and do we know that the process will pass this point, but do not know the trajectory, or we do not know
No, we
either?
know only no. The only dt is predictable. dt is non-random. So we know that our process will be located at time 3 on this circumference.
Clear.
So if you draw in polar coordinates, so if you just draw alpha and distance rho, and what happens? And oh, maybe it's like that. So if you draw t, this is distance rt. So it grows like that. And the angle t alpha t. Imagine you have a point xt yt, and that is rt. This is alpha t. So this is deterministic function, nothing random. And alpha t is something like this. If I take alpha from minus pi to pi, for example. So the distance from the origin is previsible. You can always say that in 1 year, I will be at 5 kilometers from the start. But the angle, the direction to a point is not predictable for this two-dimensional stochastic process. Okay.
Yeah, okay.
It was not required to imagine, to draw on the exam, just to clarify the structure of this process. So we have proven. So even without this, so even here we can stop and say, oh, no DW. So that was some kind of to better understand the system of equations, just to describe about the behavior, but that was not required on the exam. But just to understand that the distance from the origin is previsible, but the angle at which you allocate it is not. Okay, so thank you for today's class. We have, I hope we have corrected the mistake of the previous group and not have a new mistake. Yeah. So have a nice evening. If you have any questions, just don't be shy and ask them.
May I ask a question? So
Yes.
do I understand right that stochastic integral is a martingale like always?
Not always. We have specified that there are some technical conditions. So if you are going to do some rigorous mathematics, then it's false. But we have said that you need something like expected value of integral from 0 to t, your au squared du is less than infinity. So there are some technical conditions, but in general, if these technical conditions are satisfied, then yes, any stochastic integral is a martingale.
Okay, thank you.
Any more questions? Okay, so bye-bye. Have a nice evening.
Bye.
Thank you very much for the seminar. Goodbye.
Okay. Bye-bye.